Hi everybody. We're going to verify inverse trig identities. This is part 1. And basically we're going to use substitution. So what I'm going to do is when I see this, and you probably have already seen inverse trig identities. So if we set your inverse tan of V and set it to your angle. So that's what we're going to let happen there. And then we know that when you move the tan over, we have V equals tan of theta. So, and that's with the restriction that our angle is in between negative pi over 2 and pi over 2, or 90 and 90. Remember, you have to restrict your inverse functions. Okay, so we also know that our secant, or cosine, of theta is positive. All right, because we're in quadrant, this is in between quadrant 1 and 4. And we know cosine is positive in quadrant 4. So this is actually 1 over x. Our x is positive in between, okay, I'm just going to draw it right here. You already know this. This is negative pi over 2 to pi over 2. And cosine, or x, is positive in both quadrant 1 and 4. Okay, so based on that, we're going to set we know that tan squared of theta plus 1 equals secant squared of theta. So what we can do is say that secant times tan inverse, or inverse tan of V, we know that secant, and remember what we want. We want that. So we know that secant is going to be tan squared plus 1. So that's going to be, or secant squared. So secant squared is tan squared plus 1. So secant of theta equals the square root of 1. I'm going to move these around. Tan squared plus 1. So that's what I'm going to write. I'm going to write tan squared plus 1. And that's for my secant. All right? And so we know that tan squared, we know that tan equals B. So we know that this equals square root of 1 plus B squared. So there we have our desired result. Okay? I probably made it more complicated than it had to be, but I just try to explain everything. Okay, the same thing's going to happen here. We're going to show this, and we're going to deal with this inner function first. Set sine of V equals our angle. So actually sine inverse equals that. So V equals sine of theta. And that's just after going over your inverse functions. And we know that we're in for sine, our restrictions are in quadrant 1 and 4 again, but it can equal it because there's no asymptote. So basically, let's just write this out again. We have tan times sine, inverse sine of V equals tan of theta, which equals sine of theta over cosine of theta. So we know that sine of theta equals V, and we have that cosine of theta is going to be, if we were trying to make it look like that, so we could take the square root of 1 minus sine squared of theta for that. Because if you square root that, let me just put it over to the side here. Square root of 1 minus sine squared of theta is the same thing as square root of cosine squared of theta, which equals cosine of theta, which is what we wanted. And we know that, so I can write this as over 1 minus sine squared of theta. But my sine of theta is v. So instead of sine, I'm going to write v. So I have equals v over the square root of 1 minus v squared, which is our desired result. All right, the next set we're going to do part 2, and it's actually the same type scenario. And I'm going to do 3 of them. Thank you and have a nice day. Bye-bye.